In module 1, we presented the need for computer-aided design. In module 2, we will take an overview of how the design flows from the specification to the final packaged chip. It will be a bird's eye view taking you through all the steps. So firstly, what do we have? So what are we trying to do? We have a function or an idea or an application in mind, and that application that we have in mind have to be finally hardwired into a chip, and that chip or that hardware will realize the functionality that we have in mind. So the design flow basically composes of the steps that take the design from the initial concept to the finally packaged chip. So firstly, what do we have? That initial informal and hazy idea that we have in mind has to be formally jotted down and specified. So that is taken care by the first module here, specification. Specifications are done by, let us say, hardware description languages like, say, Verilog, VHDL, System C, etc., or are even at a higher level architecture description languages like, say, Lisa, for example, and can also be done through graphical tools like, say, spec charts or spec C, etc. And then such a specification then will be in steps taken to the final implementation. So firstly, we don't have any idea about what the structure of the chip will be, where and how, what will be the gates, what will be the architecture. We don't have that idea initially. Initially, we have only an idea of the behavior or the functionality. What function should this chip or my application perform? And we jot it down in the form of a high-level C-like program as processes which communicate among themselves. So each process could be a module, and the modules communicate among themselves, right? So we have basically a program of what we have in mind. From that, we take steps that slowly and progressively takes the design to more detailed levels of hardware structure. Finally, until we obtain the final layout or the implementation. The layout is the final software output or the design output that will be etched onto the substrate. So that is the final implementation of the design. That implementation is etched onto the substrate or is put onto an FPGA, and we get a prototype. The prototype is a design which has not all the full-fledged features of the application, but has enough so as to be able to test the design correctness as well as the implementation correctness. So we understand that the design process, what is the correctness of the design, what we intended to design has been produced as a final implementation. So that has to be verified and validated against firstly the logical output as well as also the performance goals. Is the output being produced within the correct time? Does it have the required reliability? Is it producing hotspots? Are we being able to prevent hotspots? Is it power efficient? Is it consuming power within the bounds that are specified or not? All these have to be verified on the implementation, and we do prototyping as well. And after the prototype has been found to be correct, we go for mass manufacture. The reason, as we stated in the last module, that hardware is almost irreparable after being manufactured. So we need to have zero defect designs, and the manufacturing process will produce, say, lakhs or crores of possibly of these chips. So we don't afford to have errors in the finally manufactured chips. Whatever errors are there has to be found out, debugged, and the correct chip should only be manufactured. So that is the manufacturing process. And then, as I said, up to from the specification to the implementation to the prototyping, the design goes through a synthesis process. So what is the synthesis? It is taking the design to a more detailed one from a less detailed specification. So we are at the higher levels of design, we have an idea of the functionality but have very less idea about the structure of the chip. As we go down to the details, that is synthesize the design progressively from the higher to the lower levels, we progress from behavior to the ultimate structural implementation. And at each step, it has to be validated against the performance requirements and the correctness. And also, now after we have prototyped, we have to see that the prototyped chip is error free. That means the prototyping process has the implementation taken care of all issues of the issues. We have to test it. So testing means on the implemented chip we drive certain test vectors to find out whether there are faults in the chip, right? So that is called prototype testing. And we also have manufacturing testing, which is after the final taped out chip, although they have been produced in crores possibly, but they also have to go through a minimal set of tests where certain minimal important test vectors are driven to find out whether the finally manufactured chip also is correct functionally and in terms of performance, right? So this is in a nutshell the whole design flow from concept to chip. So if we just take a toy example of what we have been taking, suppose we want to design a 1-bit full adder. So first what we have, an initial idea of what we want to do. We have two inputs A and B. We have two inputs A and B, a carry input, and we produce two outputs. One is the sum bit and one is the carry bit. It's a very simple 1-bit adder. So here, then what we do, when we have an idea of the functionality, we represent the function here directly in the form of a truth table, because this is a very simple application. And we know how the outputs will be driven. So we know that whenever there will be an odd number of these inputs as 1, the sum bit will be 1. Either all the three, if they are 1, the sum bit, all the three inputs, that is A, B and C, and if they are 1, the sum bit will be 1, or if only one of the inputs is 1, then the sum bit will be 1. And when will the carry be equal to 1? Whenever at least two of these bits are of input bits are 1, then the carry will be equal to 1. And correspondingly, we can write a program to formally represent this on a computer. Although truth table is also a formal representation, we can obtain there can be a tool which drives this takes this truth table as input and produces this program as output. But the program as such is a behavioral Verilog code which says the same thing. So the sum bit is A XOR B XOR C in or carry in, and the output is AB or AC in or BC in, right? So we said whatever we said, because the sum is an odd function, hence it's an XOR over these three. So any odd number of bits in the input is 1, the sum will produce a 1, and the carry will produce a 1 whenever at least two of the bits are equal to 1. So this is the representation of the behavior. From this behavioral representation, we slowly progress through the steps of the design process, and we'll study in detail how the design process flows. We will have what is known as this gate level design, or the logic after the logic level, after logic synthesis we will get a gate level design. This can be drawn by hand, it's very simple. but we can assume that for complex circuits, such a logic structure, such a logic circuit is difficult to design at once by hand for a complex functionality. However, the thing remains that from the behavioral description, we progress one step towards structure here, towards a logic level description of the application that we have. From that logic level application, we will have a transistor level application, transistor level design. The transistor level design here is a CMOS design of the same 1-bit full adder. So from this design, we will progress again more towards structure. This is a more structural representation. How should be the structure of this application full adder? And then this is a more detailed specification. How should these gates be implemented in the form of transistors? And then how should these transistors be laid out on the substrate? So we have this layout design. From this layout design, it will be etched onto the onto a substrate, and we will get a finally packaged chip like this, right? So this is a toy example, but provides you but shows you in a nutshell as to how the design progresses from the initial specification that we have in mind of its functionality to the finally packaged chip. Now, at any level of the design, we said that the design progresses through different stages or levels. At any stage of design, we will have what is called, the circuit will be represented in terms of a model. Okay. So, at each stage of design, the circuit is represented through a corresponding model. A model shows relevant features of the design that we require without associated details. So, we understand that well, when we are at the architectural level, we have very little idea of the structure. So, we will have a model that allows us to specify that allows us to specify what? To specify the functionality. For example, the truth table can be taken as a model. The program that we had, the Verilog code, is a model. And then the model progresses to the logic level, and then to the gate level, and then finally the physical design. So, models are classified based on two things, two aspects. So, any model at any level will be classified based on two aspects. One is the level of abstraction. So, I can have three major levels of abstraction. One is the architectural level abstraction or model, the logic level abstraction level or model, and the geometrical level abstraction or model. This figure shows these three levels. So, this is the architectural level model, this is the logic level model, and this is the geometric or physical level model, the geometric level model. And in each of these levels, there can be multiple views. For example, the architectural level has the behavioral view and the structural view on this side. So, views, we said, are of three types here: the behavioral view, the structural view, and the physical view. So, the architectural level, at the architectural level, we will have the behavioral view and the structural view. At the logic level, we will have again we'll have a behavioral view as well as a structural view, and then when we know more and more about the actual physical structure of the device, we will have at the geometric level finally a physical view as well. And the behavioral view and the structural view coincides together at the physical level, and we get a physical view of the circuit. So, let us quickly now take a look at what these basic levels or fundamental levels of abstraction are. So, the first is the architectural level of abstraction. So, at the architectural level, the circuit is modeled as a set of data computation and data transfer operations. Okay, and so this is the behavior or the function. The function is realized as a set of data computation because we have been able to represent it as a program. So, we have a set of data computations, and what does it do? Whatever computation we do in a program, basically the input data is transformed progressively to the output. So, there is a data transfer logic within the program, and this this functionality in terms of data computation and data transfer is then realized in terms of the architecture, in terms of ALU, buses, control units. So these operations as well as data transfer, these operations in terms of data computation and data transfer will then be realized in terms of an architecture of the design. So from the operations, we will first get an architecture of the design at this level. So the architecture will be in terms of the ALU units, buses, how are they connected, how are there will be control units that control operations at each time step. Okay. Then we come to the logic level. At the logic level, the circuit is represented basically as a set of logic operations, or let us say a state machine with respect to a controller and a set of Boolean equations that represent the register transfers that happen. And so these Boolean equations and state machines together will form the behavioral description at the logic level. And what will we do in the logic level? We will realize the circuit in terms of a digital circuit, in terms of gates and flip-flops. Okay, and from this one we will go through a stage of technology mapping, and finally we will have the physical components, the physical design, where we will have a completely structural view of the design, and there the circuit will be modeled as a netlist of connected geometrical entities. These geometrical entities will represent different components of the design. And then from these netlist or connected geometrical entities, we will realize the layout and or the floor plan, based on which I will finally get an image of what we have to etch on the substrate and finally obtain the packaged chip. Then we also said that at each level of design we also have views. We have abstraction levels and we also have views. So first we have the behavioral view. So behavioral view, as we have already said, it describes the function of the circuit regardless of what the implementation of the structure is. And we also have the structural view. It describes the structure of the circuit as an interconnection over components. And there is a physical view that relates to the physical objects, example transistors of a design. As we said that at the architectural level and the logic level, we know very little about the exact physical transistors or the physical level design, and we don't have the physical view essentially. However, at the geometric physical level, the structure and the behavior coincides and we get a physical view. So here is a diagram that shows the behavioral and structural views at the architectural level and the logic level. So we said that at the behavioral view at the structure at the architectural level will be composed of a program. So there is a PC plus 1, fetch something, decode something. We are writing in terms of a high level program. That high level program will be synthesized into a corresponding structure which is composed of say multipliers, adders, RAMs, control units, and an interconnection among them. This structure will basically realize the function that is shown in this behavioral view. At the logic level, on the other hand, we will have, let us say, a state machine corresponding to the controller that we have here. So the controller will basically control which operations should be executed at which time step, and hence this controller will essentially be represented in the form of a state machine. And that state machine again will be realized in terms of a gate level description, which will correspond to the structure. So the FSM at this FSM here at the logic level will represent its behavioral view, and the corresponding structural view will be this gate level description. So now if we look at the entire design flow, as we said, we looked at what we said, the important levels of abstraction as well as the views at each level, that the possible views at each level. Now, how does the design flow? The design flows through a set of synthesis processes. So what is the synthesis? It takes a design from one abstraction level to the next, from one level of abstraction to the next. The process of generating a circuit model from a less detailed one is called synthesis. And at each level, the design first starts through a specification. So the behavioral description described formally in terms of the program is a specification. That specification is synthesized. So we have this behavioral view at the architectural level here, and from this abstraction we get into another abstraction of the circuit here through this synthesis process, and we obtain a structural view. Okay, so similarly at the logic level we have the Boolean equations and the state machine, and we go through the logic synthesis process to obtain the gate level description and a minimized Boolean gate level description digital circuit after the synthesis process at the logic level. So, however, the synthesis is not a one directional thing. There can be mistakes in the synthesis at a specification level, at a given level. At any given level, at the specification can have mistakes which cannot be understood at that level until a synthesis is done. So after the synthesis is done, we may find that the design had certain errors and it needs to be corrected. So then, therefore, the design has to be taken back to the previous step, it corrected again, and then again proceed. So this is an iterative process which will go on until the design at a particular level is correct. So therefore, what we said, we need to reverse the design. So this reverse is denoted as extraction. So if synthesis takes, suppose at the architectural level, from this behavior to this structure, the extraction process will take it from this structure to this back to this behavior. At the logic level, if we have this gate level description, the synthesis will take it back to this one. And also between levels we need to get back. For example, until we go to the circuit level, let us say until we go to the transistor level, we don't understand that there is a glitch, which means that, let us say I have a gate and this gate has two inputs, and the inputs are come through a set of previous gates, and the inputs to this gate do not come at the same time, they come at different times. So for a very short period of time there is an error that is called a glitch. So a glitch says that because the two inputs to these gates do not come at the same time, the output could be erroneous. So therefore, if that can be found when the design at the transistor level has been done. Now, if we have found this, how can we correct it? We have to go back to the logic level, we have to correct the design at the logic level and come back to the transistor level design again and find out whether now it is correct, whether there are still glitches or not. Right? So this is why this extraction process is also very important along with the synthesis process. Therefore, with an overview of the entire design flow in a nutshell, we come to the end of module 2 of lecture 1.